one more section to go, and this would be section 6.4, and we're going to learn about polar coordinates. So this will be how we'll end up the semester. So polar coordinates, very interesting if you have not dealt with those before. The first thing I'm going to do is show you what the polar coordinate system looks like. So I've given an example. Down here we have a grid, and notice that you have angles in degrees. These can also be in radians. Typically they are in radians. And we also have radius like this. So a polar coordinate, you're used to having xy. Now we move to r theta in that order. So we're going to have an angle and a radius like that. Okay, so I'm going to go down, and just before we go to the next page, I'm going to show you, give you an idea of how we plot a few of these points then. So to begin with, let's say, for instance, that we have a point. Let's keep it real simple. We have a radius of 4, and let's say that we have a angle of 180 degrees. Well, we would go to 180 degrees, and then you would just count out 1, 2, 3, 4, and then you would put your dot right there. Okay, so that would be where that point's located, is out the fourth circle. Okay, another example would be 3, and let's say that we have 315 degrees. Okay, we go to 315 degrees, and from the center we count out 1, 2, 3, and then we put the dot right there. Okay, that's how you plot those. And there's a few other things we'll look at on the next page. You can also have a negative radius, and we'll look at that. Here's another system measured in degrees. And you can get these things online, all over the place. If you just Google polar grids, you'll find all kinds of different grids that you can use if you want to. Okay, on the next page, I put one in radians here, and I think the one that I provided for you is also in radians. So I'm going to use this one just because I can see it a little bit better. You can plot the points on the one that I provided for you. So this is one that's in radians, and I'm going to go ahead and just do these two examples down at the bottom, and you can do these along with me. So what we're doing on problem number 2 is we've got the point A, and we're plotting 2 and negative pi over 4. Okay, so we can also have negative angles. So what we would do on this is, we know that's negative 45 degrees. So that would be right here in the middle. Okay, that would be the same as this pole. All right, then what we'd do is we'd go out towards it to the second circle and put our dot there. So that's where point A would be located. Okay, and then the next one, number 3, we have a point B. This time we have a negative radius, and we have positive pi over 4 like this. Okay, so what we do on this is we'd start by locating the angle. Now, if you have a negative radius, all that means is instead of going towards the end of that pole, you go away from it. So you just go in the opposite direction. That's what we mean by the negative radius on that anyway. And if you think about it, on a number line that you learned years ago, that's all negative numbers really are in a number line, is they're just in the opposite direction. So you can think of this exactly the same way. So go to the angle and then go away from it, okay? All right, now I'll go to the next page. We'll just do a little bit more practice on plotting points. So I'm going to plot points on this coordinate system. So we have the point C, 245 degrees. Okay, now I've got this in radians, so we know that 45 degrees is pi over 4. So again, what we'd do on this is we'd just go to 45, and we would go out 2 radius like that, and we'd put the dot there. And then that would locate point C for us. Okay, then the next thing we got is we got the point D, negative 3, 750. So what you want to do on that? Well, first of all, you could subtract 720 from that, because that would just mean 2 laps around the circle. So all this really means is that you're going 1, 2 laps around the circle and 30 more. And of course, 30 degrees is pi over 6. So you would be on this pole right here, but since it's a negative radius, you would go in the opposite direction. So you would go 1, 2, 3, and you would put your dot there. So that's where point D is located. Okay. All right. Now I'm going to pause my recording just for a few minutes and let you work on a few of these problems. Okay, so here's what you should have done. First of all, you want to locate 7 pi over 6. So 7 pi over 6 is here. You have a positive radius, so that means you're going to go 1. Boy, and I need to zoom in on this just a little bit so I can see this a little bit better. Okay. So what I'm going to do is go there, and then I'm going to go out 1, 2, 3, and put my dot there. Okay. All right. Now we got the next point is 0 degrees. Same thing as 0. Radians would be here. You have a positive radius, so you go out 2. So that would locate point B. The next one's 2 pi. So 2 pi we know is just the same as 0. Then you would go out 2.5. So that would be like right there. Okay, out 2.5 would be where point C is located. Then the last one, you go to pi over 4. And since this one has a negative radius, you don't go towards it, you go away from it. So that point would be right in there as point D. Okay? All right. So that's how you plot polar coordinates. Very simple to do. Just remember how to handle the negative radius because that's a new idea to you. Okay. Now, as we go to the next page, what we're going to begin to look at here is rectangular coordinates and how to convert to polar and convert polar coordinates to rectangular coordinates. Something we do quite a bit in calculus for different reasons, so you'll see this again if you're taking those classes. So to begin with, we've got a couple of substitutions. If we're going to convert polar, r theta, to rectangular, we have these two substitutions. And I'll show you two things. These are not new to you guys, by the way. So notice that the cosine of theta, by definition, is x over r. Okay, well, if we just took that equation and multiplied both sides by r, you get x equals r cosine theta. So this is the definition written in a different form, see? Okay, and same thing with the sine. You know that the sine of theta is y over r. So if you multiply both sides by r, you're going to get y equals r sine theta. So see, these substitutions are just the definition of the trig functions rearranged and solved for x and y, is all they are. Now I'm going to also show you a diagram on there, to kind of a familiar diagram that we've looked at. So if you were to draw an x and y axis, and let's say that we have some polar coordinate out here. Let's say that we have something like this polar coordinate, and I'll just name that as r theta. Okay, well, if I drew a radius to that, like we're familiar with doing on a circle, you would end up having this kind of diagram like this. And then our job is to convert this to x and y. So what you'd find on this, of course, you can make a right triangle out of that, like we've been doing all semester. And the base of that triangle would be the x value. The height of that would be the y value. And of course, that would be theta, and that would be r. So really, the connection between polar coordinates comes out of this triangle diagram. It's all there for you. So the things that we know are, we know that the sine of theta is y over r. Okay, so of course that would give us that y is equal to r sine theta, like I just showed you. We also know the cosine of theta is x over r. So if we solved that equation for x by multiplying by r, we would get x equals r cosine theta. So those substitutions come from that diagram. And then we can add two more substitutions that we're already really familiar with. Is in this diagram, we know the tangent of theta is y over x. So that's a connection between theta in polar coordinates to x and y in rectangular. The other thing, of course, we know is the Pythagorean Theorem, r squared equals x squared plus y squared. So that's also a substitution. So really what you have is you have these connections right here. And you can take the square root of both sides of this equation, and of course you would get this equation like this. So that's where they all come from. Okay, so it's all from basically triangles. A right triangle diagram that I have up there, that's where they come from, all these substitutions, okay? All right, so what we're going to do next is we're going to look at changing rectangular coordinates to polar coordinates, okay? So on example number 11, what I have done is I've given you x, and I've given you y, your job is to find r theta. Okay, now one of the things I always recommend that students do on this is start by drawing a picture. I think that's real important instead of just using the substitutions, because there are a lot of times when you just easily figure this out in your head. This is an example. So if you're in an xy coordinate system, if you were to plot the point 0, -3, of course all you would do, and you already know this, is you would just put a dot down at that point 0, -3. So what you have to do is you have to find two things. You got to find the radius, and you also, of course, have to find the angle, which are really already there for you. So the radius is just the distance from there to there. So that radius is going to be 3. So that goes in there like that. And then the angle, you have two choices on the angle. Actually, we have a bunch of choices on the angle. You could say, and we want this to be in radians, it looks like, so we could say 3 pi over 2 would be that angle there. Or you could even say, if you wanted to, you could say negative pi over 2. Now, if you read the directions to the problem, it's saying these two things. It's saying use the smallest possible positive angle, which I did, and then you're also typically going to use a positive radius. But you actually have more than one way to write a polar coordinate, which is totally different than the way it is in rectangular. Rectangular, there's one coordinate for a point. It's unique. Not in polar coordinates, though. You have, since you can name angles in all kinds of different ways, and since the radius can be negative, you can name a polar coordinate literally in an infinite number of ways. And the angles, of course, could be coterminal, and you could keep adding 2 pi to it, and so forth like that. Okay, so that's how that goes. Next problem. Again, I'm going to start by doing a diagram, because I think that's always a very helpful way to approach the problem. So I'm going to go ahead over here and just draw a diagram. And all we really care about is the direction we're going. This is a rectangular coordinate system, so we're going to the right on x and down. So what I'm going to do on that is just kind of estimate this. I'm going right and I'm going down. So I have a point, which I'm going to label 2, -2√3 like that. And I'm going to draw a radius to that, like I've been doing. Okay, like that. So we got a radius. Now really what we can do is we can just make a reference right triangle of this. And anytime you do this, you always want to draw up to the x-axis. Don't ever draw the y-axis. Okay, and we're ultimately going to be looking for this theta. And if you look at this, this is really x is equal to 2, and y is equal to -2√3, like that. So first of all, if we're going to find polar coordinates on this, which is what we're after, we have to find r theta. Okay, so the way to find r, which is this part, is to use the Pythagorean Theorem. So we're going to say r squared equals x squared plus y squared. Okay, so x is 2, y is -2√3. Then we need to work out the details. So 2 to the second is 4. And this part right here, let me kind of talk about this. I sure see students messing up on this a lot. And when you're doing -2√3 squared, you really think of it this way. Now, you can learn to do this in your head. I'll tell you what I'm talking about on that. And this is not foiling. I see students foil all the time on this. And foil would look more like this. Right? Okay, now if you had that, yeah, you would, first outside, inner last, because of the plus signs. You don't do it here. You just do -2 times -2 is 4. And then you do square root of 3 times square root of 3, which is square root of 9. So you get 4 times 3, so you get 12. Okay? So what you can do, so you can do this in your head. You can do -2 to the second is 4. And then when you square the radical comes off. That's the way I do that. It's like that. See? 2 squared is 4. Radical 3 squared is 3. So you get r squared equals 4 plus 12. R squared is equal to 16. And then square root both sides, so you're going to get r equals 4. And we're going to use a positive radius on this unless I state otherwise. Okay, so that takes care of that. Then the next thing that leaves us with is finding this angle theta. And you can always find angle theta this way. You can always do the tangent relationship. So what I'm going to do on this is we're just going to say tangent of theta is equal to y. We know it's y over x. So it's negative 2 root 3 over 2. Of course, that cancels out, so you would get the tangent of theta is equal to negative square root of 3. And then what you can do is you can look up on the unit circle. That's obviously one of the points on the unit circle. So the way I kind of look at this is like this. I'm going to draw a little diagram here and just show you one way to reason this out. We've done this for a long time this semester. So basically, we're in quadrant 4. These are kind of the 3 key points. One of those points, this point right here is the point square root of 3 over 2, negative 1/2. And then this point is 1/2 negative square root of 3 over 2. So the correct one is going to be this one. So if you did y over x, and see, notice if you did this, if you did, for the point I highlighted, if you did negative 3 square root of 3 over 2 over 1/2, the 2's cross out and you're left with negative root 3. So that means that you have a 60-degree reference angle right here then. So that angle, the reference angle is 60 degrees. All right, so if we want a positive angle, and if we want this in radians and everything, that means that what we need to do is we need to give this angle, which is going to be 360 minus 60, which is 300 degrees. Okay, then you can convert that or look that up on the unit circle. So you'd have 300 pi over 180. Cross out the zeros, and then you got 30 pi over 18. You can divide by 6. So that's going to give 5 pi over 3. Okay. All right, so that gives the answer to the problem. That's what that would be in terms of polar coordinates then. All right. Okay, well, that's how that goes. Now, one thing you can do, you want to, not forget how to do your unit circle, of course, but also on a graphing calculator, if you were in, I'll just put my calculator in degree mode. Don't forget that you could, easily enough check that angle on your calculator. You could just go inverse tangent of negative square root of 3. And what you're going to find that happens on this now when you do negative square root of 3 is you're going to get a negative angle because of the range of the inverse tangent. So then you realize that the reference angle is positive 60 because the reference angle is always positive. Then you can reason out from there. But don't get too reliant on your calculator. Don't forget how to do the unit circle on that then. Okay, so those are 2 good examples of how you would work out changing rectangular coordinates to polar coordinates. All right, so I'm going to go to the next page, and I'm going to go ahead and have you work out the next 2. So I'll let you try these, change these to polar coordinates, okay? Okay, so let's see. The first one I'm going to do on this is just draw a picture. Okay, that's the simplest way to do this. So if you were plotting this in a rectangular coordinate system, of course you would be at that point 2, 0. Okay, so again, this is your given x and your given y. So if we're going to find polar coordinates, our job is to find r and theta. Okay, all you got to do is just look at it and figure it out. So the radius, you got a circle going around this in polar coordinates like that. So your radius is going to be equal to 2. And then your angle theta is just going to be 0. Okay, so that one's done. It's very quick and efficient. Your radius is 2. Your angle's 0. It's the same thing. Okay, just keep in mind that's an angle and that's a radius. So that's it. That's all you should have had to done on that. So sometimes drawing a picture is good enough. Okay, now on the next problem, I'm going to do again, the same idea. I'm going to draw a picture to kind of help me reason this out a little bit here. Whoops, I didn't mean to do that. Let's try that again. Okay, so let's see. Let's get this picture put together just so that we can visually see what's going on in the problem. Okay, now this is your x coordinate, that's your y coordinate. So you are going left and you're going up on the y-axis. And that's all that really matters on this. We don't have to draw it to scale. We're just going left and we're going up like that. Okay, then I'm going to draw my radius to that. And I need to figure that out. Okay, and then as far as the diagram goes on this, you're going to have the point, your x value is going to be negative 5 radical 3, and then your y value is going to be equal to 5. So you got to find r and you got to find theta like that. So that's what your whole focus is. And one of the reasons I like you to draw diagrams because it re-emphasizes, what you're doing in the problem and the concepts that you're connecting this to from what we learned in the past. So we do Pythagorean Theorem. We do r squared is equal to x squared plus y squared. That's how we're going to start the problem. So x is negative 5 root 3 squared. Y is 5, so that's r squared. Okay, now this part do in your head. Negative 5 squared is 25. Square root of 3 squared, the radical comes off, leaving 3. And then 5 squared is 25. So you have r squared equals 75 plus 25. So r squared is equal to 100. Then you can square root both sides, and we get r is equal to 10. Okay, so in polar coordinates, the radius is going to be 10. So that's nothing more than Pythagorean Theorem. Now there's two ways to do this, this triangle right here, to find theta. One way you can do this is you can do the tangent of theta, by definition, is y over x. So that would be 5 over negative 5 root 3. This is going to go to the unit circle. So you have tangent theta really equals negative 1 over square root of 3. Okay, now if you look at this on a basically on a unit circle, you can figure it out. Since it's got a square root of 3 in it, it's got to be one of two places, and you can figure it out this way if you want to. So you got these key points. This point right here is the point negative 1/2 square root of 3 over 2. This point right here is the point negative square root of 3 over 2 positive 1/2. Like that. So it's got to be one of the two. Well, the one that it is it's this one. And you can a lot of times just see that pretty easily in your head. And that's the one that's going to have a 30-degree reference angle to it. And see, notice on this, if you take y over x here, you would have 1/2 over negative square root of 3 over 2. That would cross out, and see, that would leave you this. Okay, so that's a 30-degree reference angle. So what we have is we have this. And then you need to give this angle, which would be 150 degrees. And then if you want to convert that or look it up on the unit circle, you have 150 pi over 180. And then you can reduce that by 3 to get 5 pi over 6. Okay, so that would be the answer you should have obtained on that problem. Okay, now I do want to, before I go to the next ideas here, I do want to run through a couple of more things here. And show you an alternative way that you could work this problem out. Now, you can do this if you want to. So one thing that you could do on this problem, and I do this pretty frequently actually on these problems, is you can actually divide these sides by 5. And if you do that, you would have this side of the triangle would be 1. This side of the triangle would be root 3. That would be negative. The x value would be negative. So you would really have a 1 square root of 3, 2 triangle, and that would be a 30-degree reference angle. So see, you can do it that way too if you want to. Now, that changes the radius. If you divide everything by 5, that changes the radius, see, but it doesn't change the angle. So that's an alternative way to putting that problem together then. Okay? All right, now we're going to do this backwards. So as I move down to the next thing, we're given polar coordinates now. So I'm giving you r and theta. Your job is now going to turn this around, and you're going to give x, y. Okay? Now there are times on these problems when you can do these in your head. Now I'm going to go ahead and show you mechanically how you do this. We have the substitution, x is equal to r cosine theta. And then we have the other substitution, y equals r sine theta. And that's all you got to remember, and then it just becomes a unit circle activity again. So plug in the radius and plug in the angle. So x is going to be 2 cosine pi over 2. Okay, and on a unit circle, pi over 2, you're up here. So you have the point 0, 1. So the cosine of pi over 2 is going to be 0. The sine is going to be 1. So that's how we can work this thing out then. So this is going to be x equals 2 times 0, which is equal to 0. So that gives that. Now you move on to y equals r sine theta. So that's going to be y equals the radius 2 times the sine of pi over 2. Well, the sine of pi over 2 is the y value, so that's equal to 1. So what you would end up with then is you would have y equals 2 times 1, which is equal to 2. So then you would have the problem solved. So that would be the same thing as the 0.02. Okay? Now, let me show you on this problem, though. You could do this problem without even having to look at a unit circle. One thing that you can do, and you can do this frequently on these problems, actually, is you can draw a diagram. I always recommend you start all these problems by graphing. So if you graphed 2 pi over 2, well, here's pi over 2, and then you would just go out to the second circle. So remember, in polar coordinates, you've got circles going around these things kind of like this, and that's enough to figure this out. All you'd have to do is figure out, okay, this point is what we're looking at right here. Well, that has an x value of 0 and has a y value of 2. So you can superimpose the rectangular coordinates over the polar coordinate system like that, and you got it. Okay, so that's it. Okay, next problem we're going to do the same way. I've given you r, and I've given you theta. So we're just going to use these substitutions. We have x equals r cosine theta. We're going to do that. Then we have y equals r sine theta. So we got that. Okay, so we're going to have x equals negative 4 cosine of negative pi over 3, which we need to look up on the unit circle. Then we're going to have y equals negative 4 sine of negative pi over 3. Okay, so just go ahead and work this out now, and I'll do, again, another triangle or unit circle diagram here. Let's kind of refer on this. So what we're looking at is we're looking at negative pi over 3. Right here, okay, so you basically got these points here. Remember, negative pi over 3 is actually negative 60 degrees. So on the unit circle, you've got this point is 1/2 negative root 3 over 2. So that means the cosine of negative pi over 3 is positive 1/2. And it means the sine of negative pi over 3 is negative square root of 3 over 2, since it's the y value. So now we're ready to complete this. So this is x equals negative 4 times 1/2, which is negative 2. Okay, so it's going to give negative 2 for our x value. And then over here, we're going to have negative 4. Y is going to be negative 4 times negative square root of 3 over 2. So that's going to be 4 root 3 over 2, or just 2 radical 3. Okay, so we've got the answer to the problem is this right here. Okay, that's the idea. All right, now one thing that's kind of worth doing on this problem too, I think it's kind of helpful to just go back and look at visually why this makes sense. To me, it's very important that you try to make sense of your answer on these. If you were plotting the point negative 4, negative pi over 3 in polar, it would go like this. So yeah, you'd be locating this pole right here. Now let me go ahead and draw a diagram on this a certain way. So you would actually be looking at this pole right here, kind of. And what you'd be doing on this is, since the radius is negative, see, here's negative pi over 3. That's where that's located. But instead of going 1, 2, 3, 4 this way, you'd be going 1, 2, 3, 4 this way, like that. So you'd be in quadrant 1. So if you look at your answer to your problem, that's also in quadrant 1. And it's got to be, okay? So that's the benefit of going through and drawing pictures, is that way you can tell you're right. I do that all the time just to make sure that I haven't made any mistakes. Okay, so I'm going to let you all work on number 17 and number 18 on the next page. So I'm going to go ahead and pause and give you a few minutes to work on 17 and 18. Okay, now this problem could have been done in a couple of different ways. To start with, I'm going to draw just a diagram to kind of see what's going on here. So that's your radius, That's your angle theta. So your angle theta is at pi. Now the thing this time is, since you have a radius of 8, you don't go towards it, you go away from it. So you would go 1, 2, 3, 4, 5, 6, 7, 8. And that's where your point would be located. So if you look at this in terms of rectangular, you already have the answer. This is the point 8, 0. So that's one way to do the problem, is just draw a picture and see if it matches, right? So pi is here, negative 8 is this way, so you would end up being on the positive x-axis. The other way you could have done this problem is you could just say x equals r cosine theta and y equals r sine theta, and you can do this without graphing. So you would have the radius is negative 8, then we'd do the cosine of pi. Well, the cosine of pi is negative 1, so you'd have 8, which, matches that, so that checks. Then we would do y equals r sine theta, so r is negative 8, and you have the sine of pi. Okay, well, the sine of pi is 0, so you'd have y equals 0, so that checks with that then. So you can do that problem either or both ways. I think it's good to do both, actually. Okay, next problem. This one you can go ahead and you can start this way if you want to. You could just say x equals r cosine theta. So that's going to be x equals 2 times the cosine of 17 pi over 6. And we need to work that out. And then we can do y. Y is going to be r sine theta. So y is going to be equal to 2 sine of 17 pi over 6, like that. So we need to work that out and figure out where that is. Now this is an angle that I'm just going to take my calculator and figure out where that is. So if I do 17 times 180 over 6, then I end up getting 510 degrees. So we're looking at 510 degrees. So if you take 510 minus 360, so 510 minus 360, not plus, minus 360 is going to give you 150. And 150 degrees is a place on the unit circle. So we're really just going to consider 150 degrees. Okay, so we're just going to do x equals 2 cosine of 150 degrees. And over here we're going to do y equals 2 sine of 150 degrees. And we just do those things together. Okay, so if I do just a little unit circle diagram over here, at 150 degrees, there's 135, there's 120, so here's 150. So you're here, so you have that 30-degree reference angle, and that point on the unit circle is negative 1/2 and positive square root of 3 over, nope, I got that backwards, okay. All right, so we're negative square root of 3 over 2, and we're positive 1/2. That's how that goes. So if we do the cosine of 150, that's going to be this. The sine of 150 is going to be the y value, so it's that. Okay, so all we'd have to do then is just work out x equals 2 times negative square root of 3 over 2. So that's x equals, the 2's cross out, leaving negative square root of 3. Okay, and then for the sine, we're going to have y equals 2 times 1/2, which is equal to 1. Okay, so that would be the rectangular coordinate. So you could use that diagram if you want to, like that. And of course what happens on this is, if you look at this point, it matches up beautifully on this, really. If you think about this a little bit, first of all, this is a quadrant 2 answer, because we're left and up. And it matches up with that triangle, basically, on that. So you can kind of think of this like this. This is one thing that I want to kind of help you reason out this problem a little bit with and see if this makes sense to you, is basically you have a radius of 2. So you're kind of on your polar, you're out to the second circle, kind of like this. So what's going on in polar in this particular problem is you have this. Okay, you're out to the second radius like that, so you have a radius of 2, right? Then you have this 30-degree angle here. And then you have this point that we just found, and rectangular, which is negative square root of 3, 1 like that. So let me show you what this means. All that means is this side of the triangle is negative root 3. That's 1. So notice we have 1, 2 square root of 3. We have a 30, 60 right triangle. So that one's actually very easy to interpret in a polar coordinate system. Okay, now, so these are the two substitutions. What we're now going to do is we're going to work with equations. So we can have equations, and you've seen all kinds of rectangular equations. An example would be y equals x squared, like a parabola, or y equals square root of x minus 4. Anytime you relate x and y, those are called rectangular equations, and they can be converted and graphed in a polar coordinate system then. So that's what we're going to begin to look at next. So the key thing is these substitutions right here. So one of the things we're going to do as we go through these problems is we have y equals x, and if we're going to change this to polar, it's actually very easy. What we do is we do two very simple substitutions. Where we see x, we replace that with our cosine theta. Where we see y, we replace that with our sine theta. So what you would end up having is you would have r sine theta is equal to r cosine theta. And then you can divide those two r's out because they don't really have any bearing on how the graph's going to work out. So you would have sine theta equals cosine theta. So our polar equation is sine theta equals cosine theta. Now, I'm hoping in a unit circle this makes sense to you, because in a unit circle, sine is y, cosine's x. So it reduces down to the same thing. So we have y equals x. We have y equals x over here. Okay? The graph of this equation is going to be a line, and it's going to have a y-intercept of 0. Okay? So let me just sort of show you kind of what's going on this on my graphing calculator. And if I put this in, if I just put in y equals x, and if I just do a standard window, you've got this. So what you're going to find on this is every point on this line, like you'll have a point 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so forth, the sine and cosine are going to be the same. And the reason is because this is a 45-degree angle. So roughly what you got going on this problem is this. Okay, you've got this line that's going through at a 45-degree angle. So that means on the unit circle, if you're looking at a unit circle, you would have the point root 2 over 2, root 2 over 2 if it's a unit circle. And that just means that's the unique point where the sine and cosine are the same. All right, so that's one way that you can interpret that problem. Okay, and even if you go down here, you have negative root 2 over 2, negative root 2 over 2. See, notice the cosine and the sine are equal. Okay, so that's what that means. Okay, next problem. Okay, we're going to start with x squared plus y squared is equal to 25. So again, what we're going to do is we're going to do our substitutions. So where we see x, we're going to replace that with our cosine theta. Where we see y, we're going to replace that with, oops, I didn't put that in there right, r cosine theta. And then we're going to replace y with r sine theta. And we're going to work it out and simplify it. So we're going to have r cosine theta squared, that's the x squared part, plus r sine theta squared, that's the y squared part, equals 25. Okay, so this is going to give r squared cosine squared theta plus r squared sine squared theta equals 25. Okay, like that. Now notice you can factor an r squared out of this, and if you do that, you'll end up having r squared times cosine squared theta plus sine squared theta is equal to 25. Okay, well, hopefully you notice that this is 1. That's that fundamental Pythagorean identity. So what we end up with then is we have r squared times 1 equals 25, or we just have r squared equals 25. Okay, like that. Okay, so that would be kind of how that one goes. Now the other thing you can do on this is you can go ahead and square root both sides, And technically you would get r equals plus or minus 5, so it doesn't really matter that you put the minus in here. You can just write the polar equation that way. It's r equals 5. Okay? So what I'm going to do is I'm going to show you, see if you kind of remember what this is. This is, from college algebra, you may recall circles. Okay, like if you have x squared plus y squared equals r squared, that's a circle with a center of 0, 0. Okay, you could also have x minus h squared plus y minus k squared is equal to r squared. That's a circle that has a center at hk. You may remember that from college algebra. Okay, so what I'm going to go ahead and do here is I'm going to let you kind of try to do this with your calculator on this. I'm going to begin to teach you as I go through these. We're going to check some of these problems in polar coordinates. So just kind of follow what I do. The first thing you want to do, if you want to graph in polar coordinates, the first thing you want to do is mode button. So you want to press your mode button. And you want to go down and to this line, you're in function probably right now, go to POL for polar and press enter. So you're now in polar coordinate mode. If you press your y equals button now, you're now going to see r equals something instead of y equals something. Okay? So for instance, in this problem we just did, we can graph r equals 5, right? And when you do the window looks a little bit different in polar. You're going to go, first of all, you set your angle. Now I'm just going to go one lap through the unit circle. You do want to make sure that you're in radian mode when you do this. So go ahead and check that. Make sure that you're in radian mode. You want to be in polar mode and you want to be in radian mode. Okay, then we're going to go 0 to 2 pi. That's just one lap around the circle. This, you want to keep that real small, 0.1. If you don't keep that small, it won't look right. Okay, this I'm just going to have you maybe keep it at -10 to 10. And, or actually, let's change that maybe to like -7 to 7. You'll probably see it a little bit better if you do that. Now let's go y, you do -7 to 7. So what you do is you set up the theta, a general rule of thumb, 0 to 2 pi, one lap around the circle, and then you set up the x and y axis the way you normally would. Now if you type graph now, you're going to see a circle being drawn. Now that looks more like an ellipse, but it's a circle, and that's because of the way the calculator does this. You can also do this zoom button, and then you can go square, option 5, and that makes it look the way it's supposed to look. So that's your graph right there that you'd end up having, okay? So what I want you to see on this is a circle that's got a radius of 5, but it's also got a center at 0, 0. Okay, like that. So that's how that goes. You can do polar coordinates. It's a pretty cool thing to learn how to do on a graphing calculator then. Okay, so let me see if this will paste my graph or not that I tried to do. Okay, so here we go. So I was going to show you a couple of things on this. On the graph that I just did. So what came out in the polar coordinate system is this. So we ended up having, in rectangular, that's x squared plus y squared equals r squared. But in polar, it's just r equals 5. And all that means is the radius is always 5. Okay, so you're kind of got that center there, and you got that radius of 5 like that. So it's a very simple equation. It just relates r. That's how that goes. Okay, that's kind of cool. Okay, now let's go to the next one, and I will let you try number 22 and 23 and see if you can convert those okay. Remember, all you do is where you see x, that's our cosine theta. Where you see y, that's our sine theta. Okay, so here is what you should have done on this problem. We've got y squared equals 16x. So where you see x, you replace that with r cosine theta. Where you see y, you replace that with r sine theta. So when you work this out, you're going to have r sine theta squared equals 16r cosine theta. All right, so we square the radius, we get r squared sine squared theta is equal to 16r cosine theta. Now, you actually can stop at that point if you want to. The simplification on these problems is it's kind of hard to tell exactly how far you go. You basically want to do your substitution and do any simple thing you see you can do. It does turn out that it's okay on these problems to divide by the radius, so you would end up getting r sine squared theta equals 16 cosine theta. And I'm just going to write the answer like that. That's probably the best way to write that. For our purposes, mainly you're just learning the substitutions. Okay, so that would be a good answer. Okay, now, whether you remember this from college algebra or not, well, this is a parabola that's opening around the y-axis. So it's basically you got something kind of going like this. Those are basic things that you learned in college algebra, so that's how that goes. Now, with this sort of a problem right here, I guess if you were going to do this one on the graphing calculator, I mean, you have to solve for r. I haven't tried this before, but let's go ahead and try this. So if you have this equation right here, you could divide both sides by sine squared theta. And then you could put this in your graphing calculator like this. So let's try it. Let's see if we get a parabola. So we go 16 cosine theta divided by, and you've got to be kind of careful about this. You've got to put the sign in parentheses, and then you've got to square it like that. So it's got to go in like that. And then if you type graph, let's see what we get. Yeah, it's parabola, like I said. Okay, so it's going to give you what you expected to get. If I zoomed out on this thing a little bit, you might even see a little bit better. Yeah, you can see the parabola a little bit better if I do that. So that's how graphing calculators work. Very cool. Okay, you can see how this system relates well to the rectangular system when you take the time to do this then. Okay, so I'm just going to take myself a little snip of this thing and put it in here just for future reference. And paste it up here somewhere. Okay, so that's it. That gives you a parabola. Okay, kind of cool. All right, now what you should have done on the next problem is this. You've got y equals 9. And again, where you see y, we plug in the substitution r sine theta. Okay, so we get r sine theta. So what we'd end up getting is we'd just have r sine theta equals 9. Now this one you can't do much on. You just go ahead and write your answer as r sine theta equals 9, and you don't have to solve it for r or anything. You can just leave it alone like that. Okay, well, from your background, one thing that you all would certainly know is if you graphed the equation y equals 9, well, what would you do? You'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you would draw a horizontal line like that. So this is basically just a line that is horizontal. Okay, now if I did this one on my graphing calculator in polar coordinates, you'd have to go like this. You'd have to solve for r. So you'd have to take this out. You have r sine theta equals 9. And if you divide both sides by sine theta, you would end up having r equals 9 over sine theta. That's how you'd have to put it in your calculator. So go 9 divided by sine theta. And then we can graph this in a standard window. So I'm just going to go zoom 6. And you're going to see that line come out like that. And that's it. Okay. So again, you can interpret these things to try to kind of make connections between the two coordinate systems. Okay, like that. Okay, so I'm going to paste this and just for future reference, and that'll give you kind of an idea of how that goes. Okay, so mainly what we're doing on this is you're learning how to convert a polar equation to a rectangular equation. That's the idea. Okay, now we're going to do this backwards. And 24, we're going to be converting polar to rectangular. And the substitutions that typically apply are going to be these. Okay? However, another thing that you want to write down is you want sometimes to introduce Gosh, I can't spell. Good thing I'm not an English teacher. Actually, I cannot sometimes write at the same time and spell. Want to introduce x. You want to basically what you want is you want to end up having r cosine theta somewhere in your problem and r sine theta. That's real big on some of these problems. Okay. All right. So let's go ahead and look at r equals 5. All right. So what we do on this is we just use this substitution up here. R is equal to the square root of x squared plus y squared, and that comes from the Pythagorean Theorem. Right, so just doing that, you've converted it to rectangular, although I think it's logical to go ahead and square both sides. So you would get x squared plus y squared equals 25. Okay, so we're going to write the rectangular equation as x squared plus y squared equals 25. Well, what is that? That is a circle with center 0, 0, and a radius of 5. Okay, and we did this same problem on the calculator a few minutes ago. So if in polar, if you graphed y equals 5, you're just going to get a circle that has a radius of 5 on it. And if you do this zoom square thing, anytime you want everything to look accurate, zoom square makes everything look exactly the way it is. And the reason is because if the default is the distance between the notches on the x and y axes on a TI calculator are not the same, and that's how you make them the same. All right, so that's how you do that. Okay, another way you could do this problem also, and I do this problem this way a lot like this, is you can actually take the equation and square both sides. So you get r squared equals 25, and then we know that that's the Pythagorean theorem, so you get that. So that's an alternative way to doing that problem. Okay, now let's move to this one. Now, one of the things that I said that's real important on this, if you see a cosine, what you really want is an r cosine, because r cosine theta is equal to x. So what I'm going to do with this problem is I want to introduce an r cosine theta there. I'm going to put that over 1, and I've got an equation with fractions. You could either cross multiply this, or you could multiply both sides by 1 plus cosine. Let's just cross multiply this. So we have r times 1 plus cosine theta is equal to 5. So I've got r plus r cosine theta is equal to 5. Right, now what we're going to do is two substitutions. All right, the first thing we know is we know this, by the Pythagorean theorem, r is equal to the square root of x squared plus y squared. Then we also know that r cosine theta is equal to x. So all we're going to do is plug it in and we're done. We don't need to do any simplifying on this problem, so I'm just going to write r is the square root of x squared plus y squared plus x equals 5. That's an answer to the problem. Okay, so I'll go ahead and highlight that and just stop at that point right there. All right, so that's how that one would go in rectangular. Now, I'm not really sure if you look at this, that's probably... well, it's quadratic in both. It's either an ellipse or a circle. It's one of the two, I can tell. So I'm going to put in polar just because I'm curious. Let's put in the polar equation. Let's put in 5 divided by, then you got to go parentheses, 1 plus cosine theta. And let's start by graphing that in a standard window and see what we get, right? It's probably an ellipse, possibly. Or it might be a parabola also, now that I think about it. Let me zoom out on that just a little bit here. It's because of the way the square root is. Yeah, it's a parabola. Okay. So, without going through the details of that, or at least let me show you this part right here. So if you did x squared plus y squared, and if you moved the x to this side and squared both sides, you would end up having x squared plus y squared is equal to 5 minus x squared. What had happened is the x squareds would cancel out. If you went through the details on this and worked this out, you would have x squared plus y squared equals 25 minus 10x plus x squared, and those would cross out, so you're left with y squared equals 25 minus 10x. That's why it's parabola. Parabolas are quadratic in one variable. The y is to a second, but the x isn't. That's how you know that that's quadratic, okay? All right, now I'm going to make a little snip of this too, and because I'd like to have this in here for reference, that is a parabola. I'm not really all that interested in the purpose of this class mostly is that you can do the substitutions. But it is helpful if you can begin to make some of these connections on these problems then. Okay, so this is the graph of r equals 5 over 1 plus cosine theta. In terms of rectangular, we got y squared equals 25 minus 10x. And you don't have to take it all the way out there. For this class, you can take it to that level right there and stop if you want to right there. Okay, so I'm going to let you do the next two. So you want to go ahead right now and pause the playback and see if you can do them, and then see, you can check my answers and see if you're right. Okay, so here's what you should have done on this one now. Now this is one you got to be really kind of careful about. And if you don't do this, you'll struggle on these problems. See, the thing is, you want this sign to really have r sine theta. You want that. So what you needed to do on this problem is you needed to multiply both sides by r at the beginning of the problem. So you get r squared here equals 10r sine theta. Now what we're going to substitute is, we know that we can substitute for r sine theta to get the answer. So r squared is going to become x squared plus y squared. Okay, then y is going to be r sine theta. Okay, so you're going to end up having the r sine theta becomes y. So you're going to have 10 times y when you plug that in. So the answer, it's okay if you just write it as x squared plus y squared equals 10y. Now this one is either a circle or an ellipse. It's actually going to be a circle. And I think the center is going to be on one of the axes. So let's put this in polar just to kind of have a record of this also. So if we go through and do 10 sine theta, like this, and graph this out, you should see a circle. And I need to change that back to a standard window and see if I can see this okay. Yeah, the center is on the y-axis. So I'm going to do this zoom square thing. So I get this, and then I'll make a copy of this too for our reference. And the reason I know it's a circle is because it's quadratic in both variables. Okay, so let me put a little, paste this thing here somewhere so I can kind of show you what I'm talking about on this. Yeah, so this one is number 27. Oh, come on. So on number 27, we had in polar r equals 10 sine theta. Okay, since you have the sign, that means that the circle is, the center is 1, 2, 3, 4, 5 there, and then you have a radius of 5 like that. Okay, so actually this that half of that thing right there, that 10 is given the distance from there to there, and then you have the sign. You guys don't have to know these structures, but I'm just kind of going through and adding this in as I teach this. What you're trying to learn how to do is convert polar equation to rectangular and vice versa. Okay. All right. Now the next one, let's see what we should do on this one is, again, when you see a cosine theta, you want it to say r cosine theta so that you can do that substitution. So if you do the distributive property, you're going to get r minus 2r cosine theta equals 1. Okay, so now we got two substitutions that we can do. We can substitute for that. We can substitute for that. All right, so r is, by the Pythagorean theorem, the square root of x squared plus y squared. our cosine theta is x equals 1. So we'd end up having the equation x squared plus y squared minus 2x equals 1. That's going to end up being a parabola again on that one. We did one like that earlier. Okay? All right, that's all I want to do on that problem. So we're now going to use our calculator to do some more polar graphs. And you can have a lot of fun with polar graphs. They're very interesting in the way some of them look. So I'm going to start by doing a graph of 4 plus 4 sine theta. And I think on your handout, I just gave you a polar grid to do, and I was going to have you do this on a calculator, and we are going to do that. But I want to show you something on this. I don't require you to know how to do this in this class, but it's kind of a good thing to go through. First of all, we're really going to graph y equals 4 plus 4 sine x. Okay, we're going to change the variables, and we're going to look at it this way. So we're going to just go ahead and break our graph up into standard scale, pi over 2, pi, 3 pi over 2, and 2 pi like that. Okay, and then we're going to make a table of values on this too as we go through this, and kind of do this in steps. Okay, so the sine of 0 is 0. The sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And back to 0 like that. Okay, now this has an amplitude change of 4. So we're just multiplying 4 times 0 is 0. 4 times 1 is 4. 4 times 0 is 0. 4 times negative 1 is negative 4. 4 times 0 is 0. Okay, well, let's go ahead and plot that one. So this was the one that's got the amplitude change. So let's go ahead and just go negative 4 and up to 4 like that. Let's go ahead and plot this in a dashed line. So you have a point 0, 0, pi over 2, 1, 4, pi 0, 3 pi over 2, negative 4, and back like that. So that takes you through one cycle of the sine wave. Okay, now what we do is we just move it up 4. So the next stage and our final stage is we're just going to add 4 to this row. So 0 plus 4 is 4. 4 plus 4 is 8. 0 plus 4 is 4. Negative 4 plus 4 is 0. 0 plus 4 is 4. So I've moved all those y values up 4, and we're going to go ahead and do that to get this graph. Okay, so I'm going to go 5, 6, 7, 8. And then I'm going to take a different color, and I'm going to go ahead and plot this then. So what we're going to have is we're going to have a point 0, 4. So I'm going to put a dot there. Pi over 2, 8. I'm going to put a dot there. Pi, 4. 3 pi over 2, 0. And then 2 pi over 2, 4 like that. Then I'm going to just connect that in. So that's going to be the rough sine wave that we have there. Now I'm also going to write these points here. So this point is 0, 4. This point here is pi over 2, 8. This point here is pi 4. This point here is 3 pi over 2, 0. And then this point here is 2 pi 4. And then I'm going to highlight these because we're actually going to move those to a polar graph. Okay, and this is kind of a methodology that's kind of interesting to have students look at. So we can actually take these points and we can plot them now in polar. So if we start with 0, 4, that would mean we go to 0 radians and we go out 1, 2, 3, 4 over, and we put a dot there. So that's dot number 1. Okay, we go to the next thing. We go to pi over 2. Then we go out to 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we got that dot. Okay. And then, let's see, if we go out to the next one, pi 4. Here's pi. So we go 1, 2, 3, 4, out like that. Okay. Then 3 pi over 2, 0. We're here at 3 pi over 2. 0 would just be dead center. And then at 2 pi 4, we're back there and we're back out like that. Well, those are how those points go in polar. Now I'm going to go ahead and do this on the calculator and show you what's really happening on this thing. If I can get the calculator to come on. There we go. Okay, so I'm going to put in, clear that off, and we're just going to put in 4 plus 4 sine theta. And we'll just do this in a standard window from like this. You want your angles to go 0 to 2 pi. Theta step 0.1. You want to keep that theta step pretty small. Now let's just go negative 10 to 10 by a scale of 1 in both the x and y direction. Okay, now let's graph it, and let's see what we get on this then. Okay, so we're going to graph this here, and if you got more and more points on this, if you transposed all these points on that sine wave, they would transport like this. So let's go ahead and let's just draw the curve like this, and I'll tell you what we call this curve. So it's doing something kind of like this, very roughly. And it kind of dimples in like that. Okay, so we have a name for this. We call this a cardioid. Okay, like that. It's called a cardioid. Looks kind of like a heart, kind of looks like a lima bean, some students tell me. Okay, well, one thing that's nice to know is it has a sine in it. Since it has a sine in it, the dimpling it's like Pac-Man. I think of Pac-Man eating the y-axis. So it's kind of like that. Okay, so that's how that goes. It's called a cardioid. One thing that's kind of interesting on cardioids, right now as I'm recording this in my little home studio that I use for music, I'm speaking through a cardioid microphone. I wish you guys could see this. Maybe I can take a picture and put it on here, because I have several settings here that are all polar. One of them is a polar pattern cardioid, which means I can pick up my voice from one direction. And when I play guitar, typically I record into a cardioid microphone because it picks up one direction, unidirectional. Omnidirectional microphones are good for a choir, or where you're picking up lots of regions around. So cardioid, that's your pickup point kind of right there, sounds coming in, and it picks that up. So if you learn about electronics, you might learn something in acoustics about cardioid microphones someday. Okay, so that's how that goes. Let's do one more like this then. And we're going to now graph 4 minus 4 cosine theta like that. Okay, so we're going to do a fairly similar thing. The first thing we're going to do is let's go ahead and do this in rectangular using the basic points. Pi over 2, pi, 3 pi over 2, 2 pi, and then let's go up to about 4, and then down to 4 like that. We're just going to plot this. What we're doing is just changing the variables. We're not changing it to rectangular. We're just changing the variables, and then we're going to superimpose this graph onto the polar system. All right. So first of all, let's do the cosine. We know the cosine of 0 is 1. Then it goes to 0. Negative 1, 0, and 1. Okay, now we have a reflection. So we're going to multiply the y's by negative. So that's negative 1, 0, 1, 0, negative 1. Like that. And then let's go ahead and just, we're going to add 4 to this actually. So let's go ahead and plot this row right here. So we have a reflected cosine. So we have this, 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 and this, and I'm going to use a dashed line. And then what we're going to do is going to move every point on that up 4. So negative 1 plus 4 is going to be 3. So that point goes there. We have 0 plus 4 is 4. So this point goes there. Then we have 1 plus 4 is going to be 5. So that point goes up. We need to add one more notch and take that to 5. Then 0 plus 4 is 4. So that point goes there. And then finally, negative 1 plus 4 is 3. So that takes us through the whole cycle. Okay, so what we would have is we would have these 5 points that we can convert and into the polar graph here. So we've got a point. I'm going to write the points down. We have 0, 4, pi over 2, 4. Now, hold on. That was a 3. So I've got 0, 3, pi over 2, 4, pi 5, 3 pi over 2, 4, and then 2 pi 3 like that. So what we're going to do is we're going to take each of these points and we're going to go to our polar grid and we're going to graph those in polar. Okay, so let's start with 0, 3. Okay, that's 0 radians, and we go 1, 2, 3 out to the third circle and put our dot there. So 1, 2, 3, right there. Okay, that takes care of that. Now the next one's pi over 2, then we go out 4. So 1, 2, 3, 4, put a dot there. Next one, pi 5. Here's pi, go 1, 2, 3, 4, 5, put a dot there. Okay, then the next one's 3 pi over 2, 4, so we're there. So we go 1, 2, 3, 4, circles out like that. And then 2 pi 3, we're just basically back to the beginning. Okay, so let's put this in the calculator and see what this does. So 4 minus cosine theta. And let's graph that and see what we get. What in the world? I put something way wrong in that. Okay, yeah, I put 2 thetas in. Well, that's an interesting graph. It looks like a ghost. So I put 2 thetas in there. I thought, what in the world did I just do? See, when you do polar coordinates, you get some crazy stuff. So let's try again. So that looks more like an ellipse. Actually, that's all that is. If you converted that over, you would get an ellipse. It's kind of boring. It's not as exciting as the cardioid, but just wait. I'm going to give you some interesting ones here in a minute. So then you would just plot that in kind of like that, and then you would have the graph of the ellipse. Now I'm going to do a zoom square on that, and this would be what it looks like. Okay. So that's a circle. I think I said ellipse. That's a circle. And it's got the center on the x-axis, okay? And that's because it's got a cosine in it, so the center would be over here. I think over like this, kind of in the middle. You've got 1, 2, 3, and then out 5 like that. So it would be here, would be where that center is, like that. Okay, now we're going to move the next page and I'm going to do one more here. This one I'm just going to do on the calculator. So let's put this in and let's see what we get. This is kind of a fun one. So let's see, 2 theta, let's put 2 theta in and see what we get. So it appears to be spiraling of some sort. So actually one thing you could do on this, and all I'm going to have you guys do is just a couple of simple things on here. It starts at in the middle, then it goes 1, 2, 3, 4, 5, 6, about like that. So just kind of estimate 1, 2, 3, 4, 5, 6, I think. And just sort of estimate that this is a spiral. So it's kind of going out like that. Now it's going to spiral out infinitely like this. So if you change your window, first thing that you can try, let's do a big angle. Like let's do, well, let's be brave. Let's do 10 pi, something like that. Keep the theta step the same. Now let's go out to like 50 to 50. And let's see if we can see more of the spiral, because actually what happens on this is it should just keep spiraling out infinitely. So let's make that negative 50 to 50 by a scale of 10. And then you can try this if you want to with me. And let's see what we get. So it should be spiraling out kind of like a spiral galaxy or something. Isn't that fascinating? So I told you, polar coordinates, you get into some really, really, really interesting things on these things. All right, so that's how that spiral is going to work out. Okay, so I'm going to, if you would like to try, I'm going to go ahead. If you'd like to try to put that in your calculator and discover what happens, I'm going to pause and give you a few minutes to do that if you want to. Okay, so I'm going to use this calculator to show you this then. So I put this in. You can try to put this in if you want to. So polar graphs can be really, really fascinating. Okay, so this is just something that I found on the internet. Whoever came up with this probably has way too much time on their hands. So I got everything set up. I think maybe there was an extra parenthesis in here somewhere, it seemed like, when I was putting this in. I think you got like this little parenthesis right here may have been extra. I'm not sure. So, because you need to have like parentheses 1 plus 0.9 cosine 8 theta, like that. I think I got an excessive parenthesis in there. So anyway, let's find out what happens. I got everything set up. I'm going to type graph, and let's see what we end up getting here. All right, drum roll, drum roll. Okay, let's see what we get. Okay, what in the world is coming out on my calculator? That is the craziest thing I've ever seen in my life. What in the world is that? So that is it. Isn't that fascinating? Okay. This one, actually, it would be called, I think, a 7-leaf rose, technically is what that is. But isn't that amazing? So I hope you enjoy polar coordinates, and I hope I'm not being a bad influence on you by showing you this graph. Of course, I don't know what that is. I have no clue what that's even trying to represent. Maybe you do, and you can tell me. Okay, so that will end up everything you need to know on this section. I'm going to slide this in here. And just kind of for future. And then that should take care of everything we need to know on polar coordinates. Okay, all right. Have a good day, and don't show this to your, go show this to your friends at a party, okay? And you'll be the life of the party. All right, take care. Have a good day.